Welcome, everyone, to this webinar. So we will start the webinar now, and I welcome you to the ChemSec webinar, where we'll talk about why highly persistent chemicals are always a hazard. And as a background, I think that there is a common belief that many people believe that as long as scientists haven't proven that the chemical is toxic, its persistence is not the problem. But I think that we also know that time and time again, we have seen that history has shown that to be wrong. And highly persistent substances have a built-in potential to cause harm. And that's what we will talk about today, why these highly persistent contaminants deserve some special attention. And to understand that, we have two speakers who will help us understand the scientific perspective of chemical persistence and also the effects caused by persistent chemicals. So Professor Martin Scheringer and Loebel from EurEau, we're happy to have you here and that you have joined and be able to present. Before we start, I would like to give just some practical stuff. Please add your questions to the Q&A. We will try to answer them in the end of this webinar, where we'll have a Q&A section. So please add your questions there. And just to make sure that everyone knows, the slides and the recording of this webinar will be sent out to everyone that registered for the webinar, to make sure that everyone has the ability to follow up and to look at the webinar. I will also very briefly introduce ChemSec. ChemSec is a Swedish NGO. We are focusing on reducing the use of hazardous chemicals. We work with companies and investors to change chemicals policy. We provide online tools to support companies with substitution. We spread knowledge and insights to relevant stakeholders. And with that, I would like to move on and to introduce the first speaker. So the first speaker of today is Professor Martin Scheringer, who is a professor at the Environmental Chemistry at Masaryk University in Czech Republic. He is also a senior scientist and group leader at the Swiss Federal Institute of Technology in Zurich, Switzerland. And he has worked on the issue of chemical persistence for over 30 years. So please, Martin, the scene is yours.
Thank you very much, Jonathan, for the introduction and the invitation to speak here. So I'll say a few words about the problem of chemical persistence, of high persistence. Next, please. We may start from a quote or with a quote from the 1970s. I will just read it out. Persistent materials, because of that property, will accumulate in the environment for as long as they are released. Since the environment is not effective at cleansing itself of these materials, they will remain for indefinite periods which were not recognized at the time of their original release. The problem could become entirely out of control, and it would be extremely difficult, if not impossible, to do anything about it. That is from Marvin Stephenson in 1977, a very early warning. And if you just go on, please, we can say this is exactly now what you see in front of our eyes. This is what has happened with PFAS in reality. It's not just PFAS. If you go on, another group of persistent chemicals, very well known, is PCBs, polychlorinated biphenyls. And there have been many reports in the scientific literature and beyond about high levels of PCBs in top predators, mostly in marine ecosystems, such as here the orca whales or dolphins or seals, and also birds and also humans. And it's stated here in this, the title of this article that was published in Science 10 years ago already, Persistent Gluten, Persistent Threats. And if we go on, we see what that actually means. Here is an orca whale that was found on the coast of Scotland. It was a female. She was 22 years old, and she had accumulated very high levels of PCBs in her blubber, in her fat or lipid tissue, of almost 1 gram per kilogram. And she had no offspring. She was infertile, and she was caught in a net. And both of these impacts on her were attributed to the PCBs because they impair the the sexual system, the reproductive system of animals and humans, and they also impair the cognitive abilities. And normally these animals are so intelligent that they can avoid nets. They are never caught in a net. So also that is attributed to the PCBs. So we see what it means if a chemical that is very, very persistent is present in environments. It is not just present, it really enters animals and humans, and it does harm. So next, please. We can ask ourselves the question, why is it then that there's still so much discussion about the meaning of persistence and whether or not persistent chemicals are a problem because they are persistent? And I would propose that a reason for that discussion and for still the pros and cons in all this is what I may call the persistence fallacy. The fallacy would be what we have here, namely that people say persistence alone is not a problem, or related, persistence indicates the mere presence of a chemical, but nothing else. But if you go on, please, we have to say persistence is never alone. There are always impacts because we are not talking about nitrogen or water or sand. Here we are talking about synthetic organic chemicals. And synthetic organic chemicals are in the vast majority of all cases at some point, at some level, toxic, or they find another, let's call it a niche in the environment where they cause harm. For example, chlorofluorocarbons, CFCs, that cause the depletion of stratospheric ozone. Then they were replaced by hydrofluorocarbons, which were strong greenhouse gases. And then these were again replaced by hydrofluoroolefins, which are precursors of trifluoroacetic acid. So even if it's not direct toxicity, it can also be a physical or chemical unwanted effect that they cause. So there are always impacts. Persistence is never alone. And therefore, the real situation is persistence indicates an impactful causal relationship that extends far into the future. If there's a persistence chemical that we release now, there will be impacts from now on far into the future. So then, if you go on, please. The actual meaning of persistence is this. It makes exposure to chemicals higher, longer, and more widespread. So it means more people are exposed to higher levels and for longer periods of time, which means persistence directly increases the occurrence of adverse effects. So we may call it a multiplier of toxicity or just a hazard in itself, because again, it's never alone and it indicates a high, at least likelihood or even a certainty at some point of effects. So I have been working on this for long, and here is now a series of slides where I show what Ian Cousins, Hans-Peter Arp, and I have called the broken record. The broken record says, avoid persistence, avoid persistence. This is in a paper that we published earlier this year. Then next, please. Another one also this year where Ian Cousins and I indicate or focus on that question of persistence being a hazard. Then next, please. There was one where that's already 8 years old now, again with Ian and with Carla Ing and Janmin Wang and myself. And here we had the word alone in the title. But now in a discussion with David Crouch from ChemSec, I also had to correct myself and say that was not the best way of phrasing it, because again, persistence in our context of synthetic organic chemicals is never alone. So it would either be per se or persistence as a proxy for other effects of the chemical is a cause of concern. Next one, please. Another paper. So there's lots of literature that represents the broken record here. Here we put together evidence from 5 cases, 5 stories of global chemical pollution. And then now on to the last one, please. That was my first paper in ESNT 30 years ago. And you see also here, I already pointed out persistence as a problem. So it has been, in a way, the story of my life. And but as long as we still have persistent chemicals on the market, I think we have to keep playing the broken record. Thank you very much.
Thank you very much, Martin, and also thank you for being persistent with the area of chemical persistence. We will now move on to the next speaker, and I would just, before that, I would like to remind you that please, if you have questions, write them in the Q&A function, and we will discuss them during the Q&A. So please put all your questions there, and we will try to reply to as many as possible. So the next speaker is Oliver Loebel from EurEau. He is the Secretary General of EurEau, which is the European Water Services Association. And he has almost 25 years of experience in European policy development. And for those who do not know, EurEau is striving to protect our water resources for the benefit of both current, but also the future generations. So please, Oliver, the scene is yours.
Yes, thank you very much for the kind invitation. Yeah, next slide, please. Very brief introduction of who we are. So as Jonathan just said, we are the European Association for representing drinking water and wastewater operators with members in 33 countries. And we are considered critical infrastructures, so very important to maintain vital societal functions. So next slide, please. Key question for us is, of course, why are we so concerned? So what is the problem with persistent and mobile substances in the water sector? So next slide. And I will also start with a quote. It comes from the Water Resilience Strategy published a year ago. Water quality and quantity are two sides of the same coin, and we must continue working on preventing pollution at source. Perfect. Urgent action is needed to tackle pollutants which pose a risk to our vital sources of drinking water, and highly persistent pollutants such as PFAS 30, they wrote, keep accumulating across EU waters and cause health impacts estimated to range between 52 and 84 billion euros annually, and this is a major source of public concern. So the problem is clearly described here, but I will still go a bit more into detail. So next slide, please, Jonathan. Yeah, so if we talk about drinking water supply, so we supply about 550 million customers in Europe, delivering 37 billion cubic meters of drinking water. Most of that water, about 60%, comes from groundwater, about 40% from surface water, and a very small share from seawater. So next slide. It's good to keep this in mind when we look further. The situation is still not too bad if we look at the current situation. So groundwater, more than 70% of the groundwater we abstract doesn't need any specific treatment or just conventional treatment like removing particles and then disinfecting. So which means we can provide a water which is natural and which is also inexpensive, affordable to private households, but also to local businesses. If you look at surface water, the share is lower, but still relatively high. Almost half of the surface water we abstract does not require advanced treatment. So next slide. What we see, the development over the past years, that these numbers are changing, and unfortunately they are changing for the bad. Why? Well, the Water Framework Directive gives a clear indication. Only 30% of our water bodies achieve good chemical status. We see that controlled source measures are insufficient. We find increasingly persistent and mobile substances and also toxic, partially, in the aquatic environment. And the promise of Article 7.3 of the Water Framework Directive that the treatment requirements to produce drinking water should be reduced sounds today like utopia. So we increase every year. And here you find a number of substances that we find in our water resources. But I will not go too much into detail here. So next slide. So what is then the problem? So if we find these substances, we see that our treatment technologies that we have in place are no longer effective. So biological treatment wouldn't work for persistent substances, which is of course a problem. And activated carbon, that which is used a lot, for example, also for the removal of pesticides, doesn't work for very mobile substances. And also most PMT, VP, VM substances are persistent to chemical oxidation, which means not only the conventional water treatment is ineffective, but also, let's say, what we call, well, today's standards for more advanced treatment is not enough to treat these and remove these substances. So next slide. Yeah, the group that, of course, worries us the most by far are PFAS, as you can imagine, mainly due to the sheer number of substances. So many thousands of different substances, many thousands of different uses, and hundreds of pathways to the environment. So there is no way to control their emission to the environment. It leads to an increasing pollution of drinking water resources. We have studies on this. We see the trends. And with the pollution of soil and drink and water resources, we also create problems not only for drinking water, but even more so for food production. And if I talk to my members, they say, well, the time it takes to re-establish the quality of a groundwater body is not 10 years. It can be 50, 60, 70 years or even more. And what is, of course, also worrying is that REACH could not prevent this disaster from happening. It was not enough. And even now, if we look at the universal PFAS restriction proposal, if we look at the best case scenario that we have, we can still expect a million tons of emissions over the next 30 years if we include pesticides, biocides, and pharmaceuticals. 1 million tons, while we measure or we have to comply with thresholds in the low nanogram range. This shows the challenge for us. Next slide. So we need to do something more to protect our water resources from persistent and mobile substances. Next slide. The impacts are clear. The more we find them in our water resources, the more and the more sophisticated treatment technologies we have to install, and the higher the cost of water services, which has, of course, a knock-on effect, not only on private households, but also local businesses. So we can decide on our side, well, we have higher costs, so we do not invest in leakage reduction anymore. Or we postpone works to adapt to climate change or cybersecurity because there are no legal requirements today. Or we say, well, let's pass the cost on to the water users. And as I said, this will hit families and businesses alike. In any event, it comes with higher energy use, higher resource use, and in many instances also with more vulnerabilities if we become more dependent on the import of certain treatment chemicals, on energy imports or so. So that's not a good situation for us. So next slide and last slide. So I would conclude clearly by calling for legislation that classifies PMT and VPVM substances as substances of very high concern. This is a basic step really to prepare for their phase out. We should also extend the generic risk assessment to all chemicals, including PMT substances, and allow for a fast-track restriction mechanism for PMT substances so that you can also apply a shortened risk assessment. This is essential really to take action fast, because once these substances are out in nature, they stay there. As I said, they stay there for decades. And last but not least, I know it's very contested, very difficult, but we call for the application of the polluter pays principle, because we think that we shouldn't shoulder the cost, neither should our customers. This should be done by those who put these substances on the market. That's, of course, provocative, and we will see in the Q&A session what you think about it. Okay, that's all from me. Thank you.
Thank you very much, Oliver. And thank you very much for being so perfectly on time, both of you. Very appreciated from our side. So we have received a bunch of questions in the Q&A. So I will post them to you, and I will distribute them, and we'll see if we have any of you can give a good answer to some of them. So I will start with this one. I think that I will start with maybe Martin for regarding this question. So do you think that the persistency criteria as defined in REACH is sufficient to identify persistent chemicals?
Basically, yes, to give a short answer. Because they, of course, they are to some extent not arbitrary, but of course, the exact numbers can be discussed and could also be different. But it is important to have these criteria. They indicate relatively long lifetimes or half-lives of chemicals in the environment. So in a way, a chemical that exceeds these half-life criteria, I think, certainly is to be considered persistent, and that is what we want. So yeah, basically the answer is yes.
Thank you. Very good and short and to the point answer. We appreciate that. So let me know if you want to say something regarding that as well, Oliver, or
no, I think this was clear. I think it refers to the CLP regulation, huh?
Yeah.
And not to REACH.
Yeah, that's correct.
Yeah.
I mean, if I may.
Yes, please.
In REACH, there is Annex 13 where the persistence criteria are defined for the PBT assessment. I think that's the connection here, but also, of course, CLP.
So we can move on regarding the persistency. I think that this again is for you, Martin. So I will take it. Maybe you can start. So persistency can be a multiplier for adverse effects, as you mentioned, which makes sense if several persistent chemicals are disposed of in one place or in the body. Is there a data that illustrates the effects of such things, or is there a way to test for these potential effects prior to use?
Prior to use, I mean, of course, there is all the testing that is required also under REACH, let's say, for industrial chemicals, and more testing, more extensive testing for pesticides. And the question also is, and as Oliver said, REACH was not able to prevent the placement of PFAS on the market. And that's also what we can confirm. We looked once at the entire list of chemicals registered under REACH, and they contain, we found about 600 PFASs on the market. In the EU, could be, let's say it's 1,000 if you missed some. And this list includes all the typical PFASs, all the typical sulfonic acids, carboxylic acids, and their precursors. So the testing was not sufficient to filter out these chemicals, these PFAS. Beyond that, the additivity of effects is also something that is known and can also be estimated. But I think, of course, it's even worse than just one chemical. So if we have more than one, and we do have many more than one chemical, but I think the concern is already about a single chemical. I mean, TFA is a case now where we see a massive increase in concentrations up to levels that may be harmful, and that is a concern per se.
There is actually a question regarding TFA. How worried should we be on TFA? I assume that you, Oliver, are a bit worried about TFA as well.
Yeah, we are very, very worried about TFA, and we are also worried about the fact that, let's say, we have no harmonized limit values in Europe. So the guidance values that we have, for example, for drinking water, vary widely from like 2.2 micrograms per liter up to 60 micrograms per liter. So we hope to get more clarity through EFSA at the end of July when they will present their new assessment. It is a very worrisome substance, first of all, because it is very persistent and extremely mobile. So all our traditional treatment technologies are ineffective, including activated carbon. So basically, we would have to move to reverse osmosis today to remove it. And this is a technology that cannot be rolled out widely in Europe. And the next reason why it's so worrying is that its concentrations in the environment are increasing so rapidly. So I think I do not know all the PFAS substances, but I think that's the one with the fastest increase in concentrations, mainly from fluorinated gases and pesticides. So we are very worried about it.
So you mentioned it, Martin. Are you worried about TFA as well?
Yeah, for the same reasons. I mean,
Yeah.
as Oliver has pointed out, this is a real concern. It's something that's ongoing, and I would even say escalating, because there are plans that a lot more of fluorinated gases will be used as heat carriers, mostly, I guess, in air conditioning for cars. And what's also worrying is really that there are replacements. There are possibilities to use other heat carriers. Of course, you would need a different technology. You would have to have a certain different adaptation of the air conditioning device. But and that is, of course, to some extent, an additional cost. But still, for all applications of fluorinated gases, or nearly all of them, there are non-fluorinated alternatives that could be introduced and used. And that's what adds to the concern, I think, that we even keep going, we as a society keep going with fluorinated gases as heat carriers, although there are valuable or viable alternatives already. And here the good question really is what is it that prevents us from making that change?
Yeah. And if I may add, when you look at the universal PFAS restriction proposal, if I'm not mistaken, the biggest emission sector under this restriction would be fluorinated gas applications, with more than 300,000 tons over the next 30 years. And most of it would be released or would degrade into TFA then. So if we are not going beyond the PFAS restriction proposal, we will still see massive increases in PFAS concentrations in the environment.
Yeah, I can only agree with you on what you mentioned. I think that I mean, we at Chemsec has worked a lot on alternatives to hazardous chemicals, and F-gases for me is, as Martin mentioned, a bit of it's hard to understand because we have alternatives. They are already on the market. So I think that that's definitely one area where there is the opportunity to get some action and to change something, because as we all know, TFA is it's a big problem, and it's also extremely persistent. So the more that we add to nature, the bigger problem we will have. But moving on from TFA, I would maybe follow up with a question for you, Oliver. So you said that around 70% of the groundwater is fine without treatment. The other 30%, is there anywhere specific in the world where the groundwater is especially polluted, or is it spread out?
Yeah. So first of all, the 70% is no treatment or conventional treatment. So it's not without any treatment. I would say it's spread out, and here we see, of course, point or local pollution events close to airports, close to army drill sites, sometimes close to landfill sites, and close to PFAS production sites or PFAS use sites. There you have local pollution, including of the groundwater. So we have cases in Sweden, in the Netherlands, in Germany, in Belgium, in France, in Italy. So that's really across the continent. So this is one thing. And you also have a difference between shallow groundwater bodies and deep groundwater bodies. So the shallow ones are increasingly exposed to very mobile substances such as TFA, whereas the deeper ones are still safe.
Thank you. Just a clarification then, maybe Oliver, for you as well, is regarding the reverse osmosis. You said that it's not able to be rolled out in Europe quickly. And what are the reasons for that is one question. So
yeah, one problem is the cost. So it would lead to a steep increase in water tariffs. The second reason is the energy use, which is very high, although it has come down over the past years, but it's far higher than for any other treatment method that we use. And the third one, perhaps the most problematic one, is the additional water use. So we would have to abstract about 20% more water, which would then be used to produce this brine, this concentrate of this concentrate water with concentrated pollutants in it. And in many regions, we do not have enough water to abstract 20% more. We would not get a permit for that. And this is not only in Southern Europe, this would be the same in Central Europe and in Western Europe.
Thank you. Still have some time left, so we'll have time for some more questions. Maybe, I don't know, Martin, I will ask you this question and see if you have a good question. Are there any particular low-cost analytical screening techniques that you can recommend to identify high persistence in chemicals? Or how do you sort of I'm just trying to rephrase the question here, but is there any good way of predicting, I would say, high persistency and persistency in chemicals?
Yes, thank you. That is, of course, a key question. And there are both approaches to do it experimentally and to estimate the persistence from the chemical structure. So we estimate or we measure. Both of them have their limitations. We may say it is relatively easy to identify chemicals that are short-lived, not persistent, and easy to degrade. And there are tests that show that. The test for ready biodegradability is one. And on the other end of the spectrum, it is also, in a way, now we know that chemicals that contain carbon-chlorine, carbon-fluorine bonds in particular, but also other structures, that they are persistent. They are difficult to degrade. So we know the extremes, and we can assign chemicals even by looking at the structure to these extremes, or we have, at least for the short-lived chemicals, we have the ready test. The difficult thing is the gray area in the middle, because often the data are noisy. There are the established OECD test guidelines, the tests according to these guidelines, but they all have their limitations. They have also challenges in the interpretation of the data, of the test outcomes. And often we find also conflicting data for the same chemical, even under the same protocol. So there is a lot of noise in biodegradation data in particular. And that has been a problem for long, that's known. We have been struggling with that problem. But again, what's important is we should be able to identify the very persistent chemicals relatively easy, again, already from the structure. So if we are concerned about particularly persistent chemicals, I think the problem is not too difficult. If you want to have persistent or half-life data for kind of all chemicals with high reliability, also in the middle ground, then that's more challenging, certainly still. But again, that should not prevent us from applying persistence criteria and classifying chemicals as persistent. And let me
Yes.
add, both approaches are needed. Both approaches are needed, both testing methods, improved testing methods, but also estimation methods that use test data in quantitative structure, in this case, reactivity relationships, to be able to predict the half-lives of new chemicals.
Thank you. So there's still some questions regarding TFA, so maybe we can just clarify this as well, maybe Oliver. So where does most of the TFA in water come from? Is it pesticides or F-gases or other sources? Do you have any data on that, or where do we stand?
Yeah, this depends on the region. So in areas where we have intensive agriculture, I would say pesticides are the main source. In other areas, it may be fluorinated gases. So I think these are the two main sources. Another source are pharmaceuticals. And then there are many other smaller sources. So they come from through many pathways, really. And it's difficult to say which one is the biggest one in each area. What is striking, for example, and this points, of course, at fluorinated gases and perhaps also incineration. In Germany, rainwater contains more than 330 nanograms of TFA per liter. And this is then used to replenish groundwater resources and provide water for the crops that we grow. So then you can imagine how the future looks like for both crops and drinking water resources, really.
And maybe we can stay with you, Oliver, because there is also a question regarding PFAS and how to clean drinking water from PFAS. I think that you browsed upon it shortly in your presentation, but maybe you can just repeat what the different techniques are for PFAS when it comes to cleaning drinking water.
Yeah, so if you look at the current legislative requirements that we have, so basically in all member states for PFAS 20, so they do not include the very short chain, ultra short chain molecules, then usually activated carbon is doing the job. The problem with activated carbon is, of course, it's fossil in most instances, and the coal comes from China, which is, of course, something that makes us vulnerable. So if you look at the more short chain substances, then you can look at, for example, ion exchange. But here, well, this is also not without problems. Because the resin itself can release hazardous substances. So you will not find a lot of this across Europe today. When we look at ultra short chain substances such as TFA, then I think the only technology which can be rolled out today is reverse osmosis, so which is also used, for example, for seawater desalination. So today, it will be mostly activated carbon.
Thank you for that clarification. So we have time for maybe one or two questions. Maybe Martin, I would put you on the spot regarding, you also talked a bit about this during your presentation, but we still also have a question regarding whether it is scientifically valid to say that persistence in all cases is negative.
I mean, what does all cases really mean? As I said, I qualified or made the qualification that we are talking about synthetic organic chemicals. And but also here, of course, we have that trade-off between, let's call it durability or longevity, which may be desired as long as a chemical or a material is in use. And then once the chemical is out of use, then this longevity turns into persistence, and that is not desired. And that is that can't be solved, that tension between these two. So in a way, of course, then the answer is no, it's not in all cases bad, but as soon as it enters the environment, then it turns into a problem. That we may say is always the case. And the question is, can we avoid the release of very durable synthetic organic chemicals into the environment? If we have to really use them, can we close the loops? Can we make the systems in which we use them really closed or as much as close as possible? That, I think, is the question.
Yes, thank you. I agree. It's not a super simple question to answer. So it's really, you really have to think about it, and it's very difficult, I think, to have a good question or a good answer to that question. So maybe one question more. So we still have a lot of questions, I would say, regarding PFAS alternatives. We have also a lot of questions regarding for polymers. I think that we will not take that into account today because we're trying to focus on persistency as a property and not what is included in the PFAS restriction. I would like to share that I think that there are definitely alternatives to what we mentioned, F gases. I think you can look at our webpage, Chemtech Marketplace, for example, to see it, to understand what are the alternatives for F gases. And also in other alternatives, there is a range of different alternatives for many of the uses of PFAS. So maybe I'll just, when we talk about PFAS, have the last question for you, Oliver. EurEau apparently is very worried about the cost of PFAS pollution. And do you have any sort of estimate of what this could mean in practice for you?
Yeah. So this will, of course, largely depend on the legislative requirements, on the thresholds that we have to comply with. But there are two useful studies, one done by the Forever Pollution Project, I think 2 years ago, and the other one was released at the beginning of this year, I think, by the chemicals unit of DG Environment. and both point at tremendous costs. So for the drinking water side, up to 18 billion per year to remove ultra short chain PFAS. Also on the wastewater side, if we add sludge management, we could come to 70 billion or more per year. So, and just to give you the total turnover that we have today, it's perhaps 110 billion. So it is massive compared to our overall turnover. But perhaps another figure is even more striking. So that's another study that was done for DG Environment. And they looked into the cost of removing 1 gram of PFAS from drinking water resources. And the cost is 27,000 euros to remove 1 gram of PFAS. Yeah, and then we compare this to 300 or 800,000 tons of PFAS that will be removed over the next years under the PFAS restriction proposal. And perhaps one more figure to confuse you even more, and that's, I still can't believe that this is true. So they looked also at CO2 emissions per milligram of PFAS removed. It's 21 kilogram, which means 21 million kilograms of CO2 emitted to remove 1 kilogram of PFAS from drinking water resources. So that's according to the study for the European Commission. It is really something that should make everybody think about the sustainability of PFAS use. So how we can justify this to society.
Yes, a very good point. I think that we have time for one more question, because I have one question here that I saw now that I also think is very interesting, and it's the question regarding how to deal with transformation products. Because in many cases we have degradation of parent compounds, and then we have this shift of persistency or half-life depending on where we are in the sort of degradation scheme. So should we assess the entire degradation pathway chemicals, or how do we sort of approach that problem? Maybe Martin have an idea.
Yes, I mean, what's stated under REACH is that transformation products should be identified for chemicals that are on the market above 100 tons per year, I think. So here, it's perhaps not the entire chain, but degradation scheme or the degradation cascade. But at least there is a request to identify important ones that may be also persistent or long-lived or at least relevant. And also the word relevant shows up in the, I think, pesticide regulation, where we have to also identify relevant transformation products that are present in a certain concentration or certain amount, certain fraction of the parent compound, and also have a certain toxicity. So transformation products certainly play an important, or can play a very important role. In the case of PFAS, it's relatively easy because there are many precursors of the PFAS that matter most in the end. So here it is really we do handle transformation products anyway when we are looking at carboxylic and sulfonic acids, because they are also transformation products of precursors. And then there are no further degradation steps for these ones. For other chemicals, as I said, it may be more work and more challenging to identify the ones and that matter, and to conduct degradation tests that really identify all the chemicals on the way down to CO2 and water. But yeah, it certainly may play a role and should not be disregarded.
Thank you. I think now we're out of time for questions. So I would like to thank you again for answering these, I would say, a lot of questions. So thank you very much for having the time also to answer the questions. So I would also like to thank the audience for the great questions and giving us the opportunity to have this discussion. Really appreciate it. And for this final part, I would like to very shortly conclude and summarize the main points that at least I take away from this webinar. And first of all, I think it's fairly obvious and important to point out that if we don't take persistency serious, that will make sure that we end up or that has made sure that we end up where we are now, which is not in a good spot, especially when it comes to the PFAS crisis. And we need to find ways to stay away and avoid future PFAS. I think that we can say that there is a rigorous scientific foundation for how to act and that we should act on highly persistent chemicals. And I think that it's also, as we have heard here, and I think the conclusion is that we can say it's unworthy for our society to not be able to provide, for example, drinking waters to our citizens and safe waters. And the only way, one of the most important ways to secure safe drinking water for the future is to remove highly persistent chemicals from the system. And with that, I would like to thank again Martin and Oliver for guiding us through this difficult topic. I would like to thank the audience for listening in, providing very interesting questions. As I mentioned before, the slides and the recording of this webinar will be distributed. Thank you again for listening in, and have a great rest of this Tuesday.
Okay, thank you.
Thank you very
Bye-bye.
much. Bye-bye, everybody.